Okay, hi everyone. You may have seen various videos of this. I guess day 10 is sort of throwing me through a loop. I've now solved it multiple times and I've forgotten to turn on my screen recording or whatnot. And then I had power outage and lots of things. So this is going to be hopefully my final video here. Let's talk about what happened. Yesterday I solved part one with graph traversal. That seemed to go pretty well. Then part two was enumerating all the graphs in there. That turned to be pretty problematic when we had a very big graph that had a trillion traversals through it. And so we ended last night with me implementing a brute force solution and then kicking it off and then going to bed. Now, a couple things happened. I woke up in the morning and it hadn't finished. My brute force solution hadn't finished. Which isn't surprising because, again, there were over a trillion combinations there. However, what did happen was I woke up this morning knowing how to solve it, which is pretty cool. It's a testament to your brain. And I talk about this in my learning course. A lot of times when we're working on something, we just want to power through it. And if you've been following along this far, you've seen that I've tried to power through things, and these graph ones have sort of thrown me for a loop here. I even, cheated. I went to Wikipedia last night and sort of thought, okay, I'll just copy an algorithm from Wikipedia, and then I just had my brute force and I sort of called it. I woke up this morning, however, knowing how to solve it. And let me give you the insight that I had. We don't want to traverse this whole huge graph that's got a trillion options in it. However, the graph has some properties that are interesting in that it can only go from the smallest number to the largest number. And so, if we have 100 numbers, we only have to hit all those 100 numbers. So this is the other insight that I had is we've got a graph, and I'm representing it as a dictionary mapping keys to values. And so if I could loop over each of those keys in order, right? I'm sort of going over each of them in order, but I kept track of how many different opportunities I had to get to that node at that point. Then I could just sum up the parent counts of how many paths through were at that point, and that would give me, at the end, it would be the sum of all the different paths through there. Let me be maybe a little more concrete. If I've got like a diamond shape here, graph, there's only one path through the first node. So by default, the first node is going to have a 1 in it. And then I'm going to split out into two nodes down here. Each of those will have the parent value, which is 1. Then we're going to combine back to the value at the bottom. So when you have more than one parent, you're going to sum the counts in each of the parents. Each of the parents had a 1 path through them, so the paths in total at the bottom is 2. But you can imagine if we have 3 parents or whatever, if we have a more complicated graph, we're just going to loop through the nodes in order, counting the sums of their parent counts, and that should be it. Okay, so in order to do this, we need one more thing. We need to get the parents. Right now, our graph is a graph of the parent to the children, so we need to make an inverted graph. Sometimes we call this an inverted index in natural language processing, but we're basically going to flip the dictionary around. So let's do this. I've got my code here. So this is where I actually got rid of my brute force implementation here. And so I deleted it, sorry. But what I'm going to do now is I'm going to create let's just run our tests and make sure that our tests run. So we're sort of starting off. Okay, so count traversals on line 101. Okay, so this does not exist right here. We're going to go stick that in here. So here's our test here, test simple. We've got our graph that we're creating. So what I want to do, what I want to do is I want to make a function that gets me the inverted graph here. So I'm going to just call this inverted, and it's going to take a graph And I'm going to use a dictionary to do this as well. And so I'm going to say that the result is equal to a dictionary. And then what I'm going to do is I'm just going to loop over the keys and the values in my dictionary and stick them in the inverted dictionary. So I can say for parent, comma, children in graph.items, and if you loop over items, you get the keys and the values. Note that children is a sequence here. And then I'm going to say for child in children, we're going to loop over every child here, and we're going to stick the child mapping to the parent as a child mapping to a list of parents. Remember, because we have like this diamond shape possibility, so one child might have multiple parents. Also note that we might have a case where we get to a child from different parents, and so we need to make sure that we don't overwrite what's in there, but we append to it. So what I'm going to do is I'm going to use the set default method of the dictionary to do that. How I'll do that is I'll say that res set default, and I'm going to set the default for a child to be equal to an empty list. Okay, so set default, if you're not familiar with it, if there is a key with that value, if there's a key with that value, no pun intended, if the key exists in the dictionary, it does nothing. If the key doesn't exist in the dictionary, then it sticks in that default value in there. Okay, and then we're just going to say res for the child as a key, and that will be a dictionary, or sorry, that will be a list. We know that there's a list in there, so we're just going to say append, and we're going to append the parent. Okay, so I think this should invert it. I'm going to say return res here. I'm going to come over to my test case, and I'm going to assert the inverted, and it's got to be day10.inverted. Of res, and I'm just going to say it's equal to an empty dictionary here, but then I'm going to go through this and inspect what's going on here. Okay, so we got an assertion error. I'm going to say --VV to see the full output. I'll scroll up a little bit. Okay, so there is the full output for our dictionary, our inverted dictionary. It's saying that the parent of 1 is 0, which makes sense. The parent of 4 is 1. The parent of 5 is 4. And then 6 has two parents, 4 and 5. So this looks like it's working. I think we're good here. If I wanted to, I could take this right here and just plop it in. So maybe I will do that. So I'll copy that, and I'll stick that in right here, just to make sure that I'm testing that. And I'll do a query replace, get rid of those new lines in there, and let's just run it again, make sure that it works. Okay, cool. Okay, so we've got our inverted dictionary. So now what we want to do is we want to count the paths through that. So let's implement that. And we can call that def count traversals. And we're going to take a graph, and then we're going to get our inverted. I'm just going to call inv is equal to inverted graph. Okay, and now remember what we're going to do here is we're going to make another dictionary that keeps track of the counts for each node. So I'm going to call that the count, and I'm just going to say that that's a dictionary, and I'm actually going to seed that. I'm going to say that the count for node 0 is 1. So you have to start at 0, and there's one way to start at 0. There's no other options there. Okay, then what are we going to do? We're going to loop over all of our index options, right? Again, this is the key insight here, I think, is that you're starting from the smallest number to the largest. So you only have to visit each of those options. So I'm going to say for I in range, and then I'm going to go to the max of graph, which is the max index there plus 1. So I want to make sure I hit that max value there, because range is the half open interval. It doesn't include the final index, and in this case, max of graph plus 1 is the value that we want to end at. Okay, now it's possible that I is not in our inverted, right? We don't have parents for I, and that's fine, right? We might skip numbers. So I'm going to say if I not in INV, we'll just continue. Okay, so at this point, we're skipping over anything that wasn't in our graph. At this point, we should be able to get parents for I. So I'm going to say parents is equal to invert I. So those are the parents for I. And then all we want to do here is we want to say that the count for I is equal to the sum of the parents. Okay, and we've got parents here. And so these are the parent indexes. What I want to do is I want to get the count at P for P in parents. Okay, and I'm just going to return count right here, and I'm going to come over to my test case here, and let's just look at what this count looks like at this point. Okay, so we asserted that the count at so here it is right down here. So the count at 0 is 1. At node 0, that's where we're starting. The count is 1. The count at 1 is also 1. The count at 4 is 1. So we're going from 1 to 4. The count at 5 is 1. We're going from 4 to 5. We're also going from 4 to 6. So the count there is the sum of the two previous ones, which is 4 plus 5. The count of 7 is 4 because we can get to 7 from 6, which has 2. We can also get to 7 from 5, and we can also get to 7 from 4. So we're summing up all those values there. The count of 10 is 4. We can only get to 10 from 7. The count of 11 is 4. The count of 12 is 8. We can get to 12 from 11 and 10. Both of those have 4, so we sum those up. We get 8, and then that's the last one. So I think this is it. So I'm going to come over here to count, and instead of returning count, I'm going to return max of count. That's going to give us the max index in there, and that should be 8 over here. Push it back up the hill. Okay, we're good there. Now I'm going to go to my larger input, and I'm not going to really, well, if I need to, I can look at inverted here, but this is the count. We already knew this from our brute force yesterday. So I'm just going to say 1928 in here and make sure that this works. Okay, so that looks like it works. Let's go crazy. We're going to go to this right here, count traversals. And I actually already have it in here. Let's, instead of doing that, since I already knew what it was here, I'm going to make it 0. And it's not running because I have a 2 here, so let's make it run. Okay, and I got this answer right here. So this is the answer to the problem, which is a very large number. What I'm going to do here is plop that in here. And this is hard to read. Let me give you a hint from Python. Python allows you in Python 3 to put underscores in there. So I'm just going to put underscores where I put commas. And we can see that this is indeed 1 trillion. So that, I believe, is our answer. And I actually already went to the website and put it in there. I got the right answer there. And so we are good with that. So let's just summarize what I learned from this. This was probably the longest series of videos that I've done so far, and not super thrilled about that, but it is what it is. You saw me sort of flounder at the traversal part. So let's just review our code here. So yesterday we did part 1 where we made our graph. and then we just got the differences in there. Part two, we made our graph. We tried to traverse it yesterday, and that worked for our small inputs. For our large inputs, it didn't work. I let it run overnight. I woke up in the morning and I had the insight that because we're using smallest numbers to largest numbers, we have to go in that order. You can't ever have a graph where you're not doing that. I can basically loop over my graph from smallest to largest and look at my parents and just sum up their counts, how many options there are through them. And if I do that, I don't have to traverse everything, enumerate all of the paths. All I need to do is sum up those values. And so this returned instantly almost. It did not require us to run it all night long. Okay, hopefully this was useful to you. I'm stoked that I woke up this morning knowing how to do it. Good luck with Advent of Code.